Hi guys, welcome back to another video in Consolidated Slice Maths. So today, I would like you to consider the following three functions. The first of those functions are x to the power of a, where a is any real number. Second is a to the power of x, where a is any number greater than 0. The third one here is x to the power of x. So I'd like you to take the derivative of each of these three functions with respect to x. The first one, I assume that you are familiar with this form, and in fact, there's a way to do this. The rule that we are using to differentiate the first one here is the power rule. So we multiply this form with a, which is the exponent, and we copy x, and then the exponent or the power is decreased by 1. And this applies for any value of a. There are separate proofs for when a is equal to a positive integer or a natural number, so you can invoke the binomial theorem. And there's a separate proof for that. So for a when it is any real number. But we're not going to cover that just yet. For the second function, it's slightly more complicated because this time the base is the constant, while the power or the exponent here is a variable. So the power rule will not apply here. So you might be wondering, how do we take the derivative of that function? To be able to do this, we have to go back a little bit. We first need to find the derivative of ln of x, which will be vital in proving how to find the derivative of this kind of form. So we're going to start off with the natural logarithm function. The natural logarithm function is the logarithm with base e, where e here is the Euler's number, and its value is 2.718, blah, 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 blah. Another definition for this number here is the limit of 1 plus 1 over h to the power of h as h approaches 0. You can also swap the h and 1 over h, and the result will still stay the same. Right, so that's a bit of an introduction to the natural logarithm function. Now, if we want to find the derivative of the natural logarithm function, we're going to have to do so using the definition of derivatives. The definition of derivative here is the limit of ln of x plus h minus ln of x over h when h approaches 0. So let's rewrite this form so that it becomes the limit of 1 over h times the natural logarithm of x plus h over x. And still the limit is when h approaches 0. Now we can rewrite this again. We can rewrite the argument inside the logarithm to obtain 1 over h times the natural logarithm of 1 plus h over x. Now we can use the property of the natural logarithm to rewrite this again and have limit of the natural logarithm of 1 plus h over x to the power of 1 over h. And now we're going to tactically rewrite this in order to invoke a power of x over h. To do that, we do this. We note that 1 over h is equal to x over h times 1 over x. So we're going to write that. So it becomes a natural logarithm of h over 1 plus x, 1 plus h over x to the power of x over h, all to the power of 1 over x, like this. Now, because the natural logarithm function is continuous near zero, not at zero, but near zero, then we can sort of interchange the limit and the natural logarithm. Well, it might seem like that visually, but what we're doing here is actually taking the limit of the function or the expression inside of the natural logarithm instead. So it looks like it's swapping in places. What we are actually doing here is the natural logarithm of the limit of 1 plus h over x to the power of x over h, all raised to the power of 1 over x. And now, notice that this form here is familiar. So h over x and x over h are reciprocal of each other. And notice that in this definition of E, we have 1 plus something to the power of the reciprocal of that something, which is equal to E. Therefore, we can rewrite this as ln of E. And then still we have to the power of 1x, 1 over x. Due to the property of the natural logarithm in E, we now know that this is actually just 1 over x. Hence, we've proven that the derivative of the natural logarithm function, or the ln of x, is equal to 1 over x. How does this relate to, now you might be thinking, how does this relate to the task of finding the derivative of a to the power of x? Well, we can go from here and find the derivative of e to the power of x, which is a special case of this function. So we have this as a result. Now let's try to find the derivative of e to the power of x with respect to x. For this one, we assume y equals e to the power of x. And what we want to find here is dy over dx. To do this, we take the natural logarithm of both sides. By doing so, we change the equation into ln of y equals x. Now, we know the derivative of the natural logarithm function for when the argument is x. If we were to make it more general, that is, we want to find the derivative of ln of some other function like this, then we can use the chain rule and have f prime x over f of x. This can be easily checked by the chain rule. Now, we want to take the derivative of both sides here. We'll obtain if we were to take the derivative of both sides with respect to x here, we'll get y prime over y. This is because y itself is a function of x. We just don't know how to, wait, hold on, we do know how to express y as a function of x. But because y is a function of x, then we have to take the derivative of y here and then divide it by y itself. Meanwhile, for the right-hand side, the derivative of x with respect to x is simply 1. And as such, y prime here is equal to y, which is equal to e to the power of x. So here we have a remarkable fact that you probably might have heard of, that e to the power of x has a derivative that is equal to itself. And this is a special case of a to the power of x. For the general case, which is the main thing that we are going to do, we rewrite a to be equal to e to the power of ln of a. As you can see, e and the natural logarithm function interact to give us just a if this were to be operated. And then there's always a power of x. We can rewrite this as e to the power of x times ln of a. Now that we have a constant multiplying the x here, we can use the chain to verify that the derivative of this function here is actually ln of a times e to the power of x times ln of a. But remember, this form here is just a to the power of x, as we just noticed. Therefore, it is actually a to the power of x times ln of a. And hence, we just figured out that the derivative of a to the power of x with respect to x for any a greater than 0 is equal to a to the power of x times ln of a. If a were equal to e, then ln of e, or ln of a, which is equal to ln of e, is equal to 1. And therefore, that is how you get how you arrive at the same conclusion that the derivative of e to the power of x is e to the power of x itself. Hence, this is our result. But now, what about the third one? For the third function, both the base and power, or the exponent is a variable. So neither of the two strategies will work. Or will they? Remember that when taking the derivative of e to the power of x here, we try to take the natural logarithm of both sides in this step. It appears that doing this is the key to taking the derivative of this function. And this technique is called logarithmic differentiation. The idea of this differentiation method is quite simple. We assume that x to the power of x here is y equals x to the power of x. And our goal here is to find dy over dx. If we try to do the same thing as last time, that is by taking the natural logarithm of both sides, we get ln of y equals x ln of x. Now, from this point, we can find the derivative of both sides with respect to x. The left-hand side becomes y prime over y, while the right-hand side becomes ln of x plus x times 1 over x, using the product rule, which simplifies to 1 plus ln of x. Hence, y prime here is the multiplication of y times 1 plus ln of x. And don't forget to substitute y back, because y is equal to x to the power of x. And there you go. That's the derivative of x to the power of x. A bit convoluted, but it works nonetheless. This logarithmic differentiation technique is very useful to find the derivative of functions of the form f of x to the power of f of x to the power of g of x. if you have this function, for instance, h of x is equal to f of x to the power g of x, then finding the derivative of h here requires us to use the logarithmic differentiation technique that we just learned earlier. So we take the derivative of both sides. And then we take the derivative of both sides now. And then we multiply both sides by h of x. So this is the most general formula for functions of this form, but I don't recommend memorizing it because it's quite messy and you are better off and you are better off just knowing how to do it. Right. So the logarithmic differentiation is quite handy to solve those kinds of different derivative problems. However, it can also be used to simplify problems of finding derivatives, a function that we also know, but would make a complete mess if we try to do it the old-fashioned way. So let's take another function. This time, I'm going to go with quite a complicated function. Right. And now I'm going to ask you to find the derivative of this function. Technically, we can find the derivative of this function simply by using a combination of the product rule and the quotient rule. However, it will be very messy and might take quite a long time, not to mention that it might be error prone. There is a way, fortunately, to simplify the work of finding its derivative. That is the aforementioned logarithmic differentiation. And I'm wondering, how can we use that? Well, let's try to differentiate both sides. Let's try to first take the natural logarithm of both sides. Now, the right-hand side might not seem any easier to differentiate just yet, but we can use the properties of the natural logarithm in order to rearrange this. So I'm going to leave it to you to verify that this simplifies to the following. So basically, anytime you see a multiplication here, for instance, 2x times e to the power negative x, you view it as two functions being multiplied together. And then because of the property of the natural logarithm, there's actually a an addition or a sum of the ln of one of the functions plus the ln of the other function. So recall that ln of a over b is equal to ln of A minus ln of B. And ln of AB is equal to ln of A plus ln of B. We can do further simplifications by realizing that ln of e to the power of negative x here is just minus x. And here, notice that the argument inside the natural logarithm is negative 5x squared plus 4x plus 3 to the power 1/2. And because we have a power inside a natural logarithm, it can be moved outside to give us 1/2 ln of minus 5x squared plus 4x plus 3. And the other terms stay the same. At this point, we can now differentiate both sides with respect to x. So the left-hand side becomes f prime over f, while the right-hand side becomes 2 over 2x minus 1 minus 1/2 times 10, negative 10 plus negative 10x plus 4 over minus 5x squared plus 4x plus 3 minus 3 second squared of 3 of x over tangent of 3 of x. Simplifying a bit further, 1 over x minus 1/2, sorry, minus 1 minus 2 minus 5 of x over 3 plus 4x squared, oh, sorry, 3 plus 4x minus 5x squared minus 3 second squared of 3x times over tangent of 3x. And now to finally find the derivative of f of x, which is now prime of x, f prime of x, we simply multiply this form, this line here, with f of x itself. Granted, this might not be very tidy, but it's probably still cleaner than if you were to do it using a combination of the power rule and the quotient rule directly. Hence, we now know that we can use the logarithmic differentiation technique to simplify the process of finding derivatives that involves a lot of functions, just like this one. And as of today, I hope you enjoy it. If you do, please leave a like and subscribe to this channel. So this is a Consultant Explains Maths episode, and bye.